So, good morning, everybody. How was yesterday? Are you tired for whole day lectures? Yeah, is it okay? So yesterday we discussed about what's the uh, desalination plan in Australia, also global plant status. Also, we learned what's the reverse osmosis membrane and then how it works. Also, we studied about what's the overall fundamental application and design was what's the system reverse osmosis consists of. So now, today, we like to continue. Oh, he's not. Okay, can you please? So we don't have to close the door, just open a little bit. This should be okay. Yeah. Yeah, open the door, is all right. Yeah. And we already have an idea about what's the seawater desalination, what's the inside, what's the osmotic pressure, what's the reverse osmosis, and what's the element and pressure buses, modules, and pre-treatment, post-treatment. So we can go through today basic reverse osmosis design by manual calculation as well as wave software calculation. So no matter what you use your computer software, you have to understand the theory behind. So we will go through first what's the manual calculation you can do, just simple and very small amount of volume we can try. And then your assignment 3 will tell you 250 million liters of day you need to design. So you need to apply for this wave software. So we can try one by one for next couple of hours. So we will have next 3 hours practicing this software. And after that, you can access anytime. Your ID can access this room, right? So during this semester, you can access to the room and anytime you can come here. Also, you can utilize your computer, laptop, and you can do your own way of design at home. So that's the how you can prepare your assignment 3, last one. So we have also consultation timing. So if you have any question, you can come and join. So we will also discuss just a bit for the week of due date of the assignment 3. Any question yesterday and today lectures? No question? So everybody looks like you're following very well. I'm very happy to see you enjoyed this last lectures. So let's try basic auto design. So this is the parameter for design of auto plant. So you need to know what's the plant capacity in terms of cubic meter per day. And you need to decide membrane properties and salt rejection because it'll depend on the feed water quality, even permeate water quality. So we ensure that the water quality in terms of Australian drinking water guidelines. So we have to meet all the criteria. And operating parameters, feed flow rate, recovery rate, module number, membrane, design, also surface area. This is all relevant to each other. So if you have this information, we can also try the one example. Okay, assume that each train has a capacity 300 cubic meter per day. So we design 300, but this can be multiplied 2 trains, 3 trains, 4, 10, 100. So this will increase the overall your capacity. So make a little bit smaller size of our design and use wave to size of RO feed pump for one train. So what conditions to use? To calculate the number of pressure buses, elements for pressure buses, total number of elements. So this is similar to your assignment 3. This is wastewater reuse, but your assignment is more about seawater desalination. So it's a little bit different, but I'm sure that you can manage this one, and then you can try your seawater desalination for your assignment. But I just want to show the wastewater reuse. Wastewater reuse is a little bit different condition. So TDS wastewater reuse is relatively low, yeah? Okay, less than 1 gram per liter or 2 gram per liter. The osmotic pressure is almost 0.8 bar. So we can apply a lot of pressure, also recover our water more than 80%, 90%. So which means when you think about seawater desalination, the osmotic pressure 28 bar and concentration is 3.5%, which means your osmotic pressure 28 bar. So we apply pressure 60 bar. So 50% recovery we can design. But if you go a little bit more than 60 bar, what has happened to the membrane? Sorry? Concentration, polarization. Also, what did you say? Ruptures. Right. Because this is a membrane module, the polymer and plastic. So this has not designed for more than 100 bar. So if you apply 100 bar or more than 70, 80, 90 bar. So yesterday I showed the telescope type of the damage of the reverse osmosis membrane module. And we have to make sure what could be the best way to set our applied pressure, because you cannot continuously increase your pressure. So seawater desalination, 60 bar, 70 bar, maximum 80 bar would be possible. So we have a 50% rejection, which means our brine concentration is almost double, right? So 3.5% increase to 7%. So 70 gram per liter of brine concentration. So how about wastewater? So wastewater initial TDS concentration is 1 gram per liter. So if you recover 50% of water, you increase only 2 gram per liter of brine, right? So in fact, you can increase more, up to 80%, 85%, potentially 90%, because wastewater water quality is relatively low TDS. So we can utilize the high recovery rate. But if you recover your feed the water 90% of recovery. So your final product of your wastewater brine is almost 10 to 15 grams per liter. So why not we can increase more, like 35 grams per liter, 70 grams per liter. So why we cannot do this? Why not we can apply 70 bars, 80 bars for wastewater reuse to increase to almost 95%, 98% of recovery? Because wastewater contain a lot of organics, also a lot of fouling. So if you increase more than 90%, so you completely clogging your outer membrane. So wastewater, we don't really go for very high TDS brine concentration. So go for almost 10 grams per liter of your brine concentration, which means around 80% to 90% of the recovery rate. So we try as an example today for water reuse our plant. So let's start design 300 cubic meter per day wastewater. So what we have to know, so what kind of membrane we can utilize? The BWR, brackish water. So wastewater is brackish water. 3400 membrane. This is one of the membrane types. So you can just decide this one as an example, but you can see from the software different membrane module elements. So you can also select some of them, but basically they are very much similar. So we just fix the BW3400 membrane element and feed water, secondary sewage effluent. And TDS is around 1.8 grams per liter. Water temperature is 25 degrees. And production volume, 300 cubic meter per day. So how we can design this one? How we can start, right? So always the design is very much a comprehensive task. So if you don't have any steps or manual, it's very difficult to where to start for this kind of design. So we can go one by one, and you can follow exactly similar pattern of your seawater desalination plant design. So we need to know about reverse osmosis system analysis. So we have 10 steps to follow all the details. Step 1, consider feed source, feed quality, feed product flow, and required product quality. So what kind of quality we have to produce, depending on your guideline. And step 2, select the flow configuration and number of passes. So yesterday we discussed about first pass, second pass. Also flow configuration, the feed water, retentate flow, permeate flow. So what kind of flow would be best way? Also flood type of the flow, or one pass flow, even circulation. Keep circulating until you achieve the high recovery rate. So we decide the flow configuration, number of passes, and select membrane and element type. So what kind of membrane would be the best to remove our standard for the water quality and element? Already we just fixed the BW3400 element, but there are many different options you have. You can try because every element has a different rejection rate, different flow rate, different also types of membrane elements. So you can select which you like it, depending on your preference, and select average membrane flux. Yesterday we talked about membrane flux. LMH is very important. liter per square meter of the membrane surface per hour. So 1 hour, how much water will be produced with 1 square meter? So we select average membrane flux and calculate the number of elements needed. So how much? I can share this one slide after today's class. So you can download. Also, yeah, feel free to take photos. Also calculate the number of pressure buses. So based on the surface area, element number, we can also calculate what's the pressure bus number and select the number of stages and select the staging ratio. So number of stages, why we need this one is increasing the recovery, water recovery. You have first stage, second stage, third stage. So you will increase the overall water recovery. Also, staging ratio. So there are several ratios. If you have a pressure vessel, let's say 5, the staging ratio would be first stage 3 and second stage 2. So if you have more than 10, so we can also select array ratio would be 5, 3, 2, something like depending on how many pressure buses. So we can allocate your pressure bus stage, how many arrangement would be the best. So we can think about staging ratio and then balance the permeate flow. The permeate flow, feed flow, retentive flow are very important to design your RO system without any problem of the operation. So we will see how we can balance the water flow depending on recovery, permeate flow, retentive. So we make sure everything is flowing very smoothly rather than we have too many permeate flow and then we don't have enough feed flow and you have a lot of fouling issues. So this is all related to your optimized operation condition, which you can save, also protect your membrane fouling, membrane operation. So that's the 10 steps we can follow if you don't have any confidence how to start. So this is the simple way. You just follow the step 1, 2, 3, 4, and you will reach to your final design outcomes. Let's go one by one, more detail. The feed water quality, flow rate, required product quality. The membrane system design depends on the available feed water and application. The system design information and the feed water analysis should be collected first. So choose the feed water source. So well water with SDI 3, surface water with SDI 5, and choose the overall feed water concentration in TDS or individual ions. The individual ion concentration from analysis always preferred because you can target how much concentration of individual ions will be removed from our software. Also, how you can measure all the detail. So you can measure from your water quality analysis lab, or if you don't have, just you can send your sample to analytical center or analytical laboratory, and they can help you to measure your samples. So if you get all the detail, we can also have a good starting water quality data to put into our software and calculate exactly how much concentration will be rejected from membrane and what's the quality of different ions we can remove. Also, osmotic pressure can decide how much recovery would be the best, and we can produce the different quality of brine. Also, brine management is important as a final waste, how we can maintain this kind of things. And second step is flow configurations and number of passes. The standard flow configuration for a membrane system is a plug flow. So you just design mostly one flow, one off flow, rather than keep circulating, because circulating always cost more for your pumping cost. Even you keep circulating water is not always efficient way. So we just design plug flow as a one-off flow system where the feed volume is passed once through the system. A RONF system is usually designed for continuous operation, and operating conditions of every membrane element in the plant are consistent with time. So we just start, and then without any stopping, unless you have a fouling issue and the chemical cleaning. So you can operate almost 24 hours, 7 days, but the flux decline, and you can try to stop, and chemical cleaning, you can go through that. A permeate stage, the double pass system is the combination of two conventional RO systems, where permeate of the first system, first pass, becomes the feed water of second system. So when you have a specific contaminant like a boron, so in your assignment, yeah, you can see some of the boron removal there. So you can have a high concentration after first pass. So in this case, you can go for second pass. So you need to decide whether I have to go first pass or second pass. And this will give you a better idea how you can manage the better quality of your water source quality. And membrane and element type. So in fact, you are not the commercial company of the membrane. So you may ask them, okay, I want to treat this kind of water quality. So which kind of membrane type and membrane element would be the best for our wastewater reuse or even desalination, because they have a already good experience. As we discussed, one element costs $500, so that they have a very good initial consultation to support what kind of membrane type would be the best from their commercial membrane element. But you can also try from your software. Software already provide different model, especially this software is from Dow Chemical, Dow FinTech. So they list out only their membrane element. Also, you can download from Torrey, even Veolia, even some membrane company, they have also similar software. So it's not only one free software. So you can also download from other company, specifically if you are interested in their membrane and membrane element. So they have a similar function of this Dow FinTech software. So you can have a selection just to utilize some other company membrane element, or this Dow FinTech membrane would be a good starting point to decide. The elements are selected according to feed water salinity, feed water fouling tendency, required rejection, and energy requirement. The standard element size for system greater than 2.3 cubic meter per hour is 8 inch in diameter and 40 inch long. And the smaller elements are available for smaller system. So when you have a large capacity, more than 2.3 cubic meter per hour, So your diameter requires 10 centimeter, 8 inch. But when you have less than 2.3 cubic meter per hour, so there is a half size, like a 5 centimeter diameter, 4 inch membrane element you can purchase. Also, there are small modules. So depending on your design, so you can decide a smaller membrane element or standard 8 inch, which has a higher uh, capacity of more than 2.3 cubic meter per hour would be useful. So in your assignment, you don't have to design for 4 inch or 2.5 inch. You just go for directly 8 inch. So you don't have to worry about the diameter, just to go for 8 inch, which is the most commercially available standard membrane element. And for high quality water application where very low product salinity required, ion exchange resin are frequently used to polish RO permeate. So ion exchange resin, it's like a sand filtration, but rather than sand, you have a resin. So this resin specifically remove some specific individual ion. So if you don't want to go for second part, if you don't want to go for membrane, if membrane cannot remove some specific ion, so you can go for ion exchange resin, which will give you also more cost effective rather than second pass, third pass. So you can see that what's the overall membrane type, TW, XLE, BW, SW, SW, HR, and nanofiltration. So this is the Dow FinTech membrane element types. So you can see that when you select membrane type TW, the TDS concentration less than 5,000 milligram per liter. So they have a different membrane module. Permeate quality will be less than 50 milligram per liter. So similarly, BW, brackish water, and FR, same as TW, so 5,000, and they have a very much similar performance for permeate quality. Even they have less than 1,000. For example, like groundwater, some of the groundwater is mixed with saline water, and you have a little bit higher than your drinking water TDS guideline, which is 500 milligram per liter. So you need to remove additional salt. So in this case, you can use XLE, LE type of element. And seawater, SW. So you can utilize this seawater, 3,000 to 15,000 milligram per liter. This will produce your final permeate quality less than 150 milligram per liter. But if you want to use more high rejection, so you can utilize SWHR. So seawater high rejection, HWHR, will be the best way for your application of seawater reverse osmosis design. So you can select SWHR, and then this is the 10,000 to 50,000. So depending on your design, so you have a less than 500 milligram per liter of permeate quality you will receive. And nanofiltration, also less than 1,000 milligram per liter, you can utilize. So just to simplify, for your design of seawater, so we can select SWHR for your assignment. But in this example, we just focus on brackish water, BW 30, 300 element type, because concentration is within this range. So we select this one for brackish water element. After that, now it's time to calculate a little bit of our average membrane flux. Yep, for 300 cubic meter per day. So how we can select this average membrane flux? The RO systems are usually designed for a specific permeate flow, liter per hour, and a specific system recovery. These numbers and specific feed water source are the information required to estimate the number of membrane element, pressure buses, and stages as flow. So select the design flux in terms of LMH. Based on pilot data or customer experience or the typical design fluxes according to the feed source from the membrane system design guideline. So if you click this one, membrane system designs guideline, so you can see, okay, this type of element has a 20 LMH is the best for wastewater reuse. Also SWHR membrane module, 40 LMH would be the best to design your average membrane water flux. So this is based on the experience. Also, this company will provide basic information of what kind of average flux would be the best. So let's say you recommend 30 LMH flux would be best, or 40 LMH would be the best for your wastewater use purpose. And then we go next one. Calculate the number of elements needed. So if we know your average water flux, 40 LMH or 30 LMH, and you can also calculate total number of elements needed. So total elements. So we have an element for 8-inch, 40-inch size of element can be calculated from this simple formula. Total number of elements needed is design permeate flow rate. What was the design permeate flow rate? 300 cubic meter per day. So we can put our design permeate flow rate and design flux. Already we got the information, 30 LMH, 40 LMH, design water flux, and active membrane surface area of selected element. So every element has different surface area of membrane. The LMH means 1 square meter of membrane surface area pass through the how much water in your permeate. So this 8-inch element model number indicates active layer. The Dow filter BW30 we decide for this element has 37. So one element contains 37 square meter in a spiral round element type. So we have information 37 square meter of active layer of surface. So we can calculate. So you put 300 cubic meter per day, your water permeate flux, design flux is 30 LMH, and put your surface area 37.2 square meter. So how many elements we can purchase? So you can design for this number of elements. After that, you have an element, let's say 100 elements you have based on your design. And next step is we need to allocate this element in one pressure vessel, right? So how many pressure vessels needed for 100 elements? So you can calculate total number of pressure vessels needed is total number of element over total number of element in pressure vessel. So we want to put one pressure vessel, 7 elements, right? So you have 100 elements. So 7 elements, you need how many 100 elements can be allocated, which means more than 10, 11, 12 pressure vessel you need, right? So 100 divided by 7. So how many elements you need? Just round off your integral. And for large system, 6 element buses are standard, or 7 or 8 is also possible. So it's up to your design and your pressure bus size. But buses with up to 8 elements available for small and compact system, shorter buses may be selected. So 6 would be best way to select. Although the approach described in the following section apply for all systems, it's especially applicable for 8-inch systems with a larger number of elements and pressure buses, which then can be arranged in a certain way. The small system with only one or a few elements are mostly designed with the element series and a concentrated recirculation for maintaining the prepared flow rate through the feed and dry channel. So if you don't have enough your water capacity, so you don't have to design many pressure vessels. So just utilize one and a little bit of recirculation would be ideal rather than you have a high number of your pressure vessels. After you select all the pressure vessels, let's say you need a 10 pressure vessels. Yeah? So how we can allocate your stages? So you need to decide number of stages. The number of stages of brackish water and seawater. So brackish water, wastewater reuse in this example. So when you recover 40 to 6%, the number of serial element position 6, and number of stages is 1. If you want to increase your system recovery, 70, 80%, 85, 90%. So you have 18 number of serial element position. Also, you can select number of stages. So depending on your water recovery, 50%, 70%, 80%. So you can decide which stage would be best for me. So if you want to increase the more higher recovery rate, so you increase the stage 1, stage 2nd stage, 3rd stage. But if you want to have 70% is good enough, so just to select only 2 stages. So in this example, wastewater reuse, I want to go for 90%. Yeah. So you can decide, I want to go 3 stages. So you have 10 pressure buses. So 3 stages, which one is the best way? 4, 5, 4, 1 would be 10 pressure buses you can allocate. First stage 5, second stage 4, last 3rd stage 1. So you have 10 pressure buses. So stage you can just allocate effective way of water recovery. But if you just want to go for 40, 60 water recovery, you don't have to go stage. Just the first stage, 10 pressure buses go one time, and you will achieve the 50% of water recovery. So breakage water, depending on your water recovery, you can decide which condition would be the best way, and number of stages of a seawater system. Now this is very much relevant to your assignment. So when you have a seawater, recovery is 40%, 50%. So you have a number of serial element position 6. The 50% is 8 to 12. The number of stages, when you just recover 35 to 40%, the first stage would be good enough. But if you want to go for more than 40% of the recovery, so you need to design second stage. So second stage, you can use 10 pressure vessel. So you can use 8 to ratio of your membrane module element pressure vessel, or you can have a 7 and 3. Different ratio you can utilize to achieve the high recovery of your seawater desalination. So depending on your system recovery, so you can select second stage, first stage. But in your assignment, I like you to design second stage because we target 45%, 50% of our overall water recovery of seawater desalination. So go for second stage of your seawater desalination plant system. So number 8, select the staging ratio. Already I mentioned about briefly this one. For a system with 4 buses in the first stage and 2 buses in the second stage, the staging ratio is the 2-to-1 ratio. We can select a 3-stage system with 4, 3, 2 buses in the first. Second, the third stage respectively has a staging ratio of 4, 3, 2. In brackish water systems, staging ratio between 2 subsequent stages are usually close to 2-1 for 6-element buses and less than that for shorter buses. So in 2-stage seawater desalination with 6-element buses, the typical staging ratio is 3.2. So when you design your staging, the wastewater reuse, we like to have a 2-to-1 ratio. But seawater desalination, we like to have a 3-to-2 ratio because our concentration, polarization, high salinity, rather than 2-to-1, so 2-to-3, the second stage received more water, yeah, so that this will give you a better staging ratio. So you design for 3-to-2 ratio of your stage for your pressure vessels. And this is last confirmation. So how we can confirm that your design is working well, or whether this is flowing well for your flow rate, for the flow. So we need to also go through this process. Step 9, balance the plumbing flow rate. It means the plumbing flow rate of A element of the system element of A concentrate. It's normally lower than the flow rate of A element. This is the difference of pressure in the right channel and the increase of the osmotic pressure on the concentrate. So there's ratio of solid flow rate of the lead element and A element can become very high on the surface level. High system recovery, high hidden salinity, low pressure membrane, high water temperature, and new membrane. The goal of a good design is to balance the flow rate of the element in the different position. So this can be achieved by the following means. Boosting the feed pressure between stages. So if you give a consistent pressure, so you will produce the consistent permeate flow. So you can have your final product and prefer for efficient energy use. Also apply or permeate back pressure. So if you have a too high permeate pressure, so you can provide a back pressure only to the first stage of a two-stage system. Lower system, cost alternative. The hybrid system use membranes with lower water permeability in the first positions and membrane with the higher water permeabilities in the last position. That is high rejection seawater membrane in the first and high productivity seawater membrane in the second stage of seawater reverse osmosis system. So you don't have to utilize only one type of membrane. So first, you can use a very high rejection membrane type. At second stage, you can select high flux membrane type. So you can balance the rejection and the flow rate, permeate flow. So you can have a saving of the overall your cost of energy as well as the better design of RO system. The need for flow balancing and the method used to balance the flow can be determined after the system has been analyzed with wave. So far, this is the steps we can follow, calculate one by one, and you will get your final outcome. And then you can start your software because your manual calculation sometimes very time consuming because you have a lot of mistakes possibly. So we want to go for this software, but you need still a little bit of rough information. Like, okay, I need roughly this many of membrane, module, membrane, pressure vessel. Okay, I need this kind of a stage I want to design. Or second part, first part, I need to design. Also, what's the final product water quality? So overall, you need to have this kind of rough idea, rough information, and then you jump to your software. Even though you don't have to make a very detailed calculation at the beginning stage, but you need to have a very rough information of what you really like to do that. And then go for your software and start one by one. So let's try. Let's try one example. This will make you clear about your software utilization. So this is conditions. Feed water source, brackish surface water. SDI is less than 5. What's the SDI? Salt density index. So why this one is important? Because let me show you what's the SDI. This is SDI. Silt density index. The SDI is calculated number based on filtration of a sample through 0.45 micrometer filter pad. The SDI readings are used to indicate the fouling tendency of water for use as the RO feed water. So which means SDI will represent what's the fouling potential. So if you have a very high SDI, You cannot utilize as a feed water for reverse osmosis. So reverse osmosis company, okay, what's the feed water pretreatment? If you have a SDI more than 5, we cannot guarantee or warranty your RO membrane because there are a lot of particles, a lot of fouling. So this will clog and this will make a lot of fouling. So you cannot produce enough water flux. So company, they like to see to make a 20 years warranty of membrane, 5 years membrane warranty when you have a SDI value less than 5, which means this is clean enough to feed to reverse osmosis membrane. So SDI is calculated by following formula. SDI 15 is 101 minus T1 over T2 over 15. So T1 is the time in second, filter initial 500 millimeter of sample. T2 is time in seconds to filter final 500 millimeter of sample. And 15 minutes is allowed to pass through this membrane between time the sample intervals. So this is very much experimentally you can calculate. So you have a more dirty water inside. So your T1, T2 ratio change after 15 minutes. The SDI 15 minutes, T1, T2, you have a high value when you have a very dirty water. But when you have a good enough, like seawater, pre-treated water, so you remove all the particles, all the fouling, and your SDI value is less than 5. So we need to give this information. Okay, we have a good pre-treatment method. Our SDI value is less than 3, 1. So it's good enough to feed reverse osmosis because reverse osmosis, the channel, water flow channel is very thin. It's around 300, around 0.5 centimeter. So if you have a particle and they keep accumulating and then clogging your channel flow, yep, which means it's not only about the membrane fouling, so you will clog your channel flow, yep. So making sure that the SDI has to be less than 5, which is the good quality of water you will receive from your RO element. So this is the information we need to get for this SDI value. And required formula flow 720 cubic meter per day. The 6 element pressure buses to be used. So we target this 75% recovery. So let's design this one based on our 10 steps. Yep. So first step, brackish water supply water with the SDI less than 5. The formula flow rate is 720 cubic meter per day. This is first step. Already we have a very good feed water source and SDI value is less than 5. So this is good enough to pass through our RO feed water. And second step is the flow configuration. So we select the one pass, only one flow rate for the RO membrane element. Select plug flow type. And we select, this is brackish water. So FIMTech BW30. So this has 34 square meter of membrane surface area. So this is given by the membrane manufacturing company. So you don't have to know one element, how many. But in general, it's only 30 to 35 in between. So you can put very rough data, 33 or 35 or 30. So that's good enough to assume the active layer in 80-40 inch of the one element. So we have a 34 scale method. The recommended average flux from the surface area, surface supply water feed with STI less than 5 is 25 LMA. So this company, within this condition, breakage water and BW30 membrane element, so they recommend or they can suggest so 25 LMA. Also, yeah, you can increase a little bit or decrease a little bit, but in general, you just think about breakage water. Your flow rate average flux is 25 to 30. And total element can be calculated. So we have a total capacity 720 cubic meter per day we want to design. And we have your flow rate. This is in terms of liter per hour, 41. And this is the surface area of the membrane, 33. And average flux, 25 LMA. So how many elements we need for this condition? 35. So we can calculate 35 elements we need for designing this 720 cubic meter per day of brackish water. What's the next step? Total number of pressure vessels. So we want to put 6 elements or maybe 7. You can decide. So 6 elements we like to include for one pressure vessel. So you have a 5.8. So which means 6 pressure vessels we need. So 6 pressure vessels we can utilize. So what's the stage we like to select? So 6 elements stage, 75% recovery stage. Because the water recovery is 75%, we like to have 2 stages rather than 1 stage, because 1 stage will give a lower water recovery. So we select 2 stages. And how we can arrange the ratio, staging ratio, we already discussed about seawater desalination, 3:2 ratio would be ideal. Breakage water or wastewater reuse, 2:1 ratio is ideal for the staging of this pressure vessel. So we like to have a 2:1 ratio, which means we have a 6 pressure vessel. So we have to make sure 6 our pressure vessel. So 4:2. The first stage we put 4 pressure vessel, and then second stage we put 2. So you have a first stage, second stage, and total number of pressure vessels 6, so that you can get the 4:2 ratio. So this is you can start in terms of your water capacity, water recovery, membrane, your number and pressure vessel. And the chosen system must then analyze using the WAVES computer system, because you want to know your ammonia concentration is good enough, or nitrate concentration, or heavy metals. Okay, there are heavy metal in your groundwater, brackish water. So you put your individual ions inside the software. So this membrane will calculate how much rejection you will achieve for your single ions each. So you just go for more detail. This is very rough design by calculation. So you have a feeling like, okay, when you design 720 cubic meter per day, which is equivalent to Central Park. So there is a Central Park, they treat brackish water, wastewater around 1,000 cubic meter per day, right? So which means, okay, 1,000 millimeters per day in Central Park, this kind of site, we may need around 7 or 8 pressure vessels. Then recovery will be 80%. And you need this kind of membrane RO system design. So that's exactly, you can also have a good initial assumption for your capacity and membrane module. So you have gas, like 1,000 cubic meter per day. Central Park may need 8 pressure buses. So we can achieve 80% recovery. Also, we can design for this membrane element. And now you can also make a more detailed information from the software. Very easy, right? So far, everything is okay, right? Any questions so far? So this is a basic math. We have tried as a simple number, but now it's let's go for a little bit complicated software, but it's not really complicated. So you can easily achieve the data from this software. So how many people already installed this software? Everybody, any problem for your installation? No problem, right? But you can utilize this computer any time. So you can come and open the door. You can do your assignment. If you cannot access the laptop, and we go for one by one. So this is the screen of web software. So you can see the reverse osmosis membrane design. In fact, your assignment could decide ultrafiltration. So already I discussed with you. You have two options. One is the center filtration, dual media filter, one treatment. Second option would be ultrafiltration and RO. So you can decide one of them in your design of the seawater desalination. So if you like to do ultrafiltration, so you can simply click this one and then move to the in front of RO. So it's connected to each other. Yep. So you can easily hybridize the ultrafiltration in front of ultrafiltration system. So you can design in your software from pretreatment, ultrafiltration, followed by reverse osmosis. But if you want to design multimedia filter, you have to calculate manually. So you can have like a filtration system, what's the flow rate, what's the size you need. So you can easily calculate depending on the surface area of and flow rate. So if you want to design multimedia filter, so there are many resources in the internet how to calculate multimedia filter design. So you can easily calculate very simple method using the other sources. But if you want to go for ultrafiltration, you can utilize this software. Even you don't have to include this ultrafiltration. Just to put the arrow, and then you completely separate ultrafiltration. So it's up to you. So you can select one of option. And this feed flow rate you can put here and whatever you like. In this case, there are many different polishing, demineralization. So you don't have to look at all the different technology. This is like a resin or absorption or some of the ion change filter system you can incorporate. But at this moment, in this class, you don't have to learn other technology. Just focus on ultrafiltration RO. But ultrafiltration is not in this class. Just we focus on RO because ultrafiltration is very much a simple way of the flux calculation. So we don't want to go for this ultrafiltration in this class. But it's up to you. When you design, you can decide multimedia filter or ultrafiltration as a treatment for reverse osmosis. So we just want to focus on reverse osmosis here. So seawater. So in this feed water, you never ever put 250 million liter per day because your scenario tells you want to design 250 million liter per day for sediment desalination plant. However, you don't put the whole capacity in this feed water capacity volume. Just you fractionate and you multiply with your fractionated your design, and then you can have more easily calculate for your design. So let's say you want to design 250 megaliter per day. So I want to design 50 megaliter per day or 10 megaliter per day and multiply your over 250. So here, just to one train design, this is not whole capacity. This is one train, 10 megaliter per day or 1 megaliter per day. Yeah. So you design only small part of your membrane system. So you put like a 72 or whatever you want to design for your membrane module. And you want to show us a product. So when you design 250 million liter, this is permeate flux. It's not feed water. So which means your production is 250 million liter per day, not your feed water 250 million liter per day. So permeate final product is our target, which means you need to produce your product water 250 million liter per day rather than feed water. So 50% recovery. So how much feed water you need to calculate. So you can think about what's the best way to utilize the feed water. And second tab. So you can see the home. It was home at the previous slide. And this is feed water. This is the reverse osmosis and summary report. Yeah. So we have a feed water here. So as I mentioned, step one was you collect your water quality, your guideline of farming quality. So you need to think about what's the water quality in your water. So if you know what's the water quality, so stream one, stream two, you don't have to worry about this one. Only focus on one stream because sometimes your water source could be several streams. So 50% from here, 30% here, but you don't have to put this one because sometimes your water quality keep changing different stream, but we don't have to consider that scenario at this stage. So feed water. So you like to put water type is seawater or wastewater or brackish water. And subtype with conventional pretreatment. The conventional pretreatment means multimedia filter. The center filtration is conventional one. Also, you can click there and you will see ultrafiltration, pretreatment, or some other pretreatment. You have options. So what kind of pretreatment you can utilize for this reverse osmosis membrane? And you need to put the turbidity. What's the turbidity? What's the TDS, total suspended solid? So already I mentioned about SDI 15. SDI you calculate less than 5 or more than 5, you're not supposed to utilize the reverse osmosis. So you must do less than SDI 15.5. So SDI is around 5. Organic content, seawater is almost 1 milligram per liter. Wastewater is 10 milligram per liter. So you can decide based on your region. Temperature. So what temperature you have to put? So minimum, maximum, and design. So you can put the temperature. So this is the 28 degree, 29 degree. So we just average for design one because the gap is not that much big. But if you have a very big gap, better to have a little bit lower temperature design. The pH around 8 for seawater. And individual ion, so you can include one by one. So your scenario at the end of your appendix, you can see the quality of individual ion for seawater in your design parameter. So you can put the ammonia concentration, potassium concentration, sodium, magnesium, calcium, based on your scenario information rather than other information. Yeah. So you can utilize our scenario water quality, seawater data. But here, this is the only example for brackish water. So let's put, sorry?
Let's say 25 degrees Celsius is 7.
7. pH is
There is 8.
Okay, this is example, not exactly same as our scenario. This is another example. I don't want to go exactly the same scenario. So this is example. You have to put your data from scenario in your assignment, right? So we have an individual ion. So you can input your data in this individual ions and cation, anions, and then neutrals. Yeah. So if you put cation, anion, neutral, because some of the water quality data you don't know because you cannot measure every individual ion inside water. So you may get the unbalanced cation, anion, electrical charge. So this system will balance automatically. So whatever you know, put in this software, whatever you know, as many as possible. So this will give you a better result. So you put all the cationic result, anionic result, and you have neutrals. So because this information will tell you what's the rejection of ammonia, what's the rejection of sodium, individual ion from your membrane type. So you will get also better outcome when you have more information. So this is the information you have total dissolved solid, charge balance, and estimated conductivity. So based on this information, we go also next step. But here, we need to also put some of the important information. If you don't know this one, you cannot calculate what's the inorganic scaling, fouling potential in your water quality. So temperature, induced viscosity, determine pumping requirement. The pH and alkalinity properties are linked. pH control is critical to control pretreatment coagulation and scale formation. So when you have a high pH, so you need to change the pH. So this pH will give sufficient also information of your scaling formation. So when you have a different pH and different fouling potential. So we need to also put pH. Also, alkalinity is a requirement to control pH. So we have a carbonate, bicarbonate. Some of the alkalinity was good information to look at the calcium carbonate, calcium phosphate, also some of the magnesium carbonate fouling potential. So if you know what's the alkalinity concentration of the water, give you more detail. Fouling potential. When you concentrate your water more and more, so when is the timing, or you may have a calcium carbonate fouling potential. So this software will calculate this kind of information. So if you give a pH and alkalinity, so this is the ideal to look at the inorganic fouling potential. And TDS influence the RO operating pressure. So TDS will give you overall dry and osmotic pressure. So which pressure will be best to recover 50% of the recovery rate. So this is the physical property you better to include in your software as a minimum. Inorganic inputs. So calcium, magnesium will be the one of the strongest inorganic potential. So if you can put this information, calcium, magnesium, so you will have a better idea, scaling formation. Also sodium, potassium, osmotic pressure, corrosion, absorption ratio, also barium and the strontium, slightly soluble metals, a special problem for RO due to sulfate salt solubility limit. Barium sulfate, strontium sulfate easily attached on the membrane, and you have a problem of the fouling. So if you have a barium and strontium ion concentration, so this software will also calculate what's the fouling potential from this material. Also silica, present in water, silicate, SiO2, also soluble. Fouls are at concentration 100 to 200 milligram per liter. Also bicarbonate, carbonate, and chloride, hydrogen sulfate would be the good information. If you put into your water quality data, you will get the good potential fouling. Of course, if you don't know, you don't have to put, but they will not show what's the potential of this membrane fouling in terms of your water recovery. Already SDI, we discussed about this one. And second step is also reverse osmosis. So already we tried 720 cubic meter per day require 8 pressure vessel. And then we go for 2-to-1 ratio and 6 pressure vessel. So now we design 70,000 cubic meter per day. 700 was the 6 pressure vessel we need, brackish water, right? And this is the 70,000, which means almost 100 times more. So you may need 100 times more element, more pressure vessel. So you have this kind of feeling, and then you can design what's the number of stages, first stage or second stage. So you can decide which stage would be the ideal. The flow factors. So what's the flow factor is that you have a very new membrane. So your flow factor is 1. Whatever you receive, your membrane is very new, so you will have a best performance of our overall design, right? But after 1 year, your membrane is found. Your performance flow factor is not exactly what you design here. So you consider after 1 year, we decreased around 10% of overall permeate flux. So you put in this case 0.9. So you design okay, your membrane lifetime is 5 years in general. Yeah. So you design for average, let's say 5 years. So you may have membrane fouling 2.5 year around 20% decrease, right? So 20% flow factor is 0.8, right? So in this case, you can put the 0.8, but you have a very good quality of feed water, which means your flow factor increased. You don't have much problem or damage of the overall membrane for next 5 years. So you can put 0.9. So your flow factor design will tell you overall average your membrane, yeah, how many water flux will be jeopardized for the next couple of years. So you design for average way of this fouling potential. So flow factors, temperature, permeate back pressure. Permeate back pressure, you don't have to use this one because this is a real practical application purpose. So you don't have to in your design for your water. So just to leave as it. You don't have to know much about this one. And you can put the feed flow rate 75,000 cubic meter recovery. I want to go for this is seawater 43%. Permeate flow rate is 32,000 cubic meter per day. The flux membrane is around 16 LMH. This is seawater desalination. So before we try with brackish water. So at the time, the flux was 35 LMH, but now this is the seawater quality. So flux is around, we decide the 16 LMH and concentrate recycle flow. We don't go for recycle flow. You don't have to circulate the, and then permeate split. So when you have a permeate, you want to mix with some of the feed water of the RO system. So you may utilize this one, but in your assignment, even you don't have to use a split of permeate, just to put the zero and put also your concentrated recycle flow. So roughly you calculate the element for pressure. So we want to put 7 elements in one pressure. So we select SWRO30 for the seawater desalination. The total number per stage, we need around 2,000 elements for this water volume. And pre-stage pressure, stage back pressure, we don't have to put this one. And you will see in this condition, what could be the outcome you will receive. And then what's the individual ion, you can get the rejection, what's the flux balance from this region. So what membrane already, we have a discussion about this one, so I will skip. And this is those, we discuss about what's the TDS level, BWRO, SWRO. And this is what's each membrane element in a vessel has to operate within certain limit. So to minimize the concentration polarization, so permeate flow rate below upper limit, and element recovery below upper limit, and concentrate flow rate above lower limit. So you have an element, so there are certain limit for the minimum flow rate and their flow rate suggestion. So you can make sure that all the membrane element follow this kind of limit for the flow rate. Also, to avoid the physical damage, feed water flow rate below the upper limit, and pressure drop below the upper limit, and then feed pressure below upper limit. So you need to make a good balance of your feed water, pressure drop, and feed pressure, which means you don't have to damage your overall physical damage. So using this software, also you need to check feed flow rate per parcel in first stage has to be in between 8 to 12 kilometers per hour. Otherwise, if it's too fast, you don't have enough time to permeate your water, right? So this is the suggested your feed flow rate, also concentrate flow rate. So you have a feed, then recover your water, and then decrease your concentrate flow rate. So almost at the later stage of your element, so your flow rate last stage more than 3.6 cubic meters per hour. We need to design. So this is the basic, like our element. They have a small channel, and this channel, when you flow the only feed flow rate 8 to 12 cubic meter per day, and the concentrate at the last stage 3.6 cubic meter per hour would be ideal for your software design. So individual element recovery. Yesterday already we tried. First one 12% of recovery. Second one decrease 10%. Third one decrease again 9%, 8, 7. So it decreased a little bit from each element. So always we maintain individual element recovery between 8 to 14%. So this will combine together, and then finally you recover water more than 50%, 60%, 90% of the water recovery. So this is the reverse osmosis system design. You can see you have several back pressure here, split the permeate, and this is your first stage, and this is the second pass. So you can have also diagram for your membrane RO system design. So in your assignment, okay, you design for your membrane second stage and second part, yep, and try to show this diagram. Then we just identify, okay, you design this condition and stage 1, stage 2. And in fact, you don't need a back pressure here. Also, you don't have to put this kind of chemical. Just you don't have to put the split of your second pass. So just to show your seawater desalination, 45% recovery. We just utilize second stage, second pass. So you will see the diagram of second pass, second stage way of diagram from this system configuration. So you design everything now. You get the information of water quality. You design how many elements, pressure boxes, yeah. First pass, second pass, first stage, second stage. So you put all the information in this system. You have also several options to change the pH or add anti-scalar based on the report. So you can also select for your configuration and chemical adjustment. The pH you can decrease to 6 for seawater desalination. Also, you can utilize degassing because the seawater contains a lot of CO2 and carbonate. So you can degassing your water and anti-scalant. So based on your report, final summary of report, you will get your data, or you need to put anti-scalant because you have a fouling potential of this value. So in this case, you can just put some of the anti-scallop from this software. So if you change the pH, so your water chemistry change, then fouling potential possibly removed. So that could be the good example to find out the problem and then solve from this kind of uh, chemical adjustment. So let's say, what's the carbonate scaling potential? So this software will identify several fouling potential. One of the important indication is carbonate scaling, because the seawater contains very high concentration of carbonate. So carbonate concentration is always occurring at the end of a stage. So they are very easy to detect this carbonate scaling. So how they detect this one is based on the LSI scaling potential, Langelier saturation index. So LSI scaling potential, you can see from the software, but what's the theory behind is negative less than zero, no scaling potential. Water will dissolve calcium carbonate, so you don't have any scaling issue. But this LSI value is positive, greater than zero. Scale can form, calcium carbonate precipitation may occur. So that's exactly, if you put your alkalinity, carbonate concentration, calcium, magnesium, and this software will detect, okay, in this water recovery condition, you will have a strong fouling potential, calcium carbonate, magnesium carbonate. So you need to put the alkalinity, calcium hardness, as well as the total dissolved solid and pH and temperature. So LSI value is equal to pH minus pHs. So pH, if you have a pH lower, you have a negative value, right? If you have a pH high, you would have a positive value of LSI, which means fouling potential, positive is high. So you remember the pH of the seawater is 8. But we like to decrease pH 6 because of this LSI. So if you have a high pH, you can easily form your calcium carbonate and the carbonate scaling potential. So whenever you have a lower pH, you will get the good fouling prevention. So pHs is equal to 9.3 AB minus CD. What's ABCD is? A is the TDS concentration. So you have more high TDS, you have a less, because minus value is the pHs. So you have a high TDS, you may have a less membrane fouling. Hello? Yeah?
We have assignment today.
Huh?
So it's studying engineering.
Yeah.
And the spring is already installed in this lab, right? And we have an assignment today.
Sure. So you can use that. Okay, that's fine.
They are already installed in these two.
Only this two. Okay, you can sit. Yeah,
Is it
yeah,
okay?
I think so. Yeah. Sorry, they want to use some other software, not our software. So due is very soon. So if we agree, let them first do their assignment. It's not relevant to our subject. So pH A related your log value of the total dissolved solid. So if you have a high pH, your A value is the high, so pH value is the high, which means you have a more negative LSI value, which means fouling potential is low. So if you have a high TDS, this will interfere your calcium magnesium fouling potential so that you can reduce the overall your LSI value. B value also depending on your temperature. So you have a high temperature, you have a high solubility. So your calcium carbonate potential is less. So you need to have a high temperature. How about C value? Log 10 calcium concentration. Absolutely less calcium concentration is the best way. Also D, alkalinity. So you have a high alkalinity, you have a high potential. Less alkalinity, you have a less LSI value, negative value, so that you will reduce the overall your fouling potential. So LSI, pH minus pHs can be calculated automatically from the software if you provide alkalinity concentration, calcium, magnesium concentration inside your software. So if you want to know detail about this fouling potential, you must put inside your individual concentration. Otherwise, this will not provide this value. So that's how they calculate this kind of information. And you just click after you input all your necessary information. So you click this tab, summary report. The summary report will give you all the data. So I want to see from your report as the appendix. So you can attach you can also print out from the PDF file. So PDF file can be generated from this report. So you just click after you design everything. I want to see your design report. If somebody exactly same as your design, something I don't want to see. So everybody has a different way of the design. So you cannot be exactly the same as your two report. I want to see as an appendix. So you don't have to put into the main report because main report you just summarize how many, was a little bit of important information you can capture from the configuration of system. And just to mention about, okay, please report to the appendix A, our summary report. So I will look at your summary report. Then I can identify whether you design well or whether you just utilize the resource from the inside our example. So you can see if you open the file, there are several examples of seawater desalination, wastewater, brackish water. So you can refer to it. That's fine. But make a change of your way of design so that I can better understand how much effort you put in this report and your design and your assignment. So you click this one and you can print out for PDF file, export to PDF, and you can attach the OLED to your appendix, right? And then I can cross-check this one. So you see the system configuration, how you design, and this will show you all the detail. What's the flow rate change? What's the TDS initial pressure? What you like to put inside? The description, flow, TDS pressure. So number 1, 2, 3, 4, 5 point configuration will show all the different your conditions. And our system overview. So you have a train, you have also what's the recovery rate, and you design first pass, second pass, and I can see all the parameters, how you design the active layer, what's the module, what's the pressure boxer, what's your second pass and second stage, third stage. So I can see all the detail of your information from this report. And You will see also what's your overall pass of the first stage level and feed water condition, concentrate condition, permeate condition. At the same time, each individual ion will show initially how much concentration you have, and then we change the pH. The concentration change a little bit, and you have a stage 1, stage 2. What's the concentrate change also? And permeate. So you have a permeate concentration, stage 1, stage 2, and your overall permeate. So I can see all the each individual rejection from this report. So I want to specifically you target on boron. The boron concentration has to be less than 0.5 milligram per liter. So when you design first pass, your boron concentration would be higher than your drinking water guideline or your design parameters guideline. So your concentration, you can see all the detailed individual ion rejection, especially boron concentration at the permeate level. You need to make sure less than this concentration. So I can see all the individual ion from your report, and then I can also see whether you design the detailed target of this kind of individual compound. And design owning. So software will show you owning. So as I mentioned, most of owning are from flow balance. So feed flow, concentrate flow, permeate flow. So some people give too much feed flow, too less feed flow. So you cannot balance this mass balance. So they have a lot of ownings, mostly in this system design. So I like you to remove this owning. So if I see your report, I like to see none. Yeah. So that you design and solve the problem for your designing. So if you have designing, you go back again, then we change your parameter of design and then make sure your design only is nothing here.
Like, where are we competing in stake or it will be?
Yes, it is show your feed flow rate is too high. Your permeate flow is not balanced. So you can change the module number or flow rate number or recovery number. Sometimes, yes, you can use back pressure because of your permeate is too high. So in this case, permeate back pressure give a little bit of solution of this design owning. So it's up to you. You can change a little bit of balance the way of the flow rate number. But if you have a problem, or I cannot solve this problem, make it simple. Let's design of maybe 1 cubic meter, or I gave you an example of 720 cubic meter per day. So make a smaller design of capacity. If you have a more capacity, you have a more element, more pressure vessel, more stage. So you have a more design only. But if you have less, like a 10 pressure vessel, then you can guess and you can design. So if you have too many vessels, flow, design owning is keep coming out. Yeah. So in this case, make a smaller one. I don't want to let you just to keep trying to suffer with the very high volume of your design, because this is a learning stage. You can make it simple, make a very small number of volume, which already we try as a hand calculation. So first you hand calculate and then put into this software and then see. And this will give you a better idea rather than a lot of design owning. So if you have ownings, please go back and make a simplify or reserve your design and make sure you don't have warning sign in this report. And you can see also all the detail of flow rate and then this kind of information. Also solute concentration, second pass. So your point 1, 2, 3, 4, 5 from the system configuration. So this report will show you every point, detailed information. So I want to see also every detail. So this is the solubility onyx. So this is also very important. I prefer not to have this solubility onyx in your report, but this is not avoidable. So you can show as it is. Because this is not up to you. It's up to your report. Because potential is already happening. So what happens is that, okay, if you design such a way, you will see stiff index, Langelier LSI index, magnesium hydroxide saturation point is higher than your 100%. Anti-scalant may be required. So your report will show you LSI value is positive. And your magnesium hydroxide is oversaturated in certain point, 1, 2, 3, 4, 5. So in fact, this is the information. Okay, I want to put the anti-scalant. I want to reduce the pH. I want to reduce you can do something to remove this potential, ideally, practically, but this is, you don't have to do this one in your report, just so you can see what information you get. Of course, you don't have to change much about this reduction of solubility owning sign, just to understand, okay, after pass 1, we have a plus more than 0. So LSI value 0 has a very high fouling potential. Much higher fouling potential, 1.57. Sorry. Minus value, less fouling potential. And out of second pass concentrate, less fouling potential. So based on this information, the red color will tell you, okay, what kind of fouling potential you have, and how we can resolve this one. So that's I want you to understand what's the information you get from this report. That's it. So you can try today. Now you can start incorporate your data and start design. So you can practice from the example file in the software and then understand first. And if you have any question, please let me know. So this QR code shows yesterday our lectures. We just recorded from the screen. So sometimes the voice may not be very clear because I just move around. So if a voice is not clear, yeah, you can just understand. This is not the best quality I record, but it's better than nothing. Yeah. So also I just recorded this on screen. So you can also come back from this YouTube and video, and we can also send the email, communicate through and online or just email anytime. Yeah, please let me know. And today, maybe after today or tomorrow, I will upload the today lectures. So you can expect maybe tomorrow or tonight rather than today from our lecture. So any question so far?
So I have just one general question.
Yeah.
If it is dissolved, then how come it's solid? When we talk about TDS,
Mm-hmm.
if it's dissolved.
Mm-hmm.
Why do we call it solid?
Solid, total dissolved solid. Okay. Dissolved mean like you dissolve the vitamin, like organics. So some of inorganic compound, they have a plus minus charge, cation anion. But for example, like urea, it's dissolved as an organic, but there is no charge. And that's still as a solid, like vitamin organics, even some of the urea, they are easily dissolved in water, but they are not like ions. Right? So we just say combine everything. TDS measure basically their electrical conductivity.
It's not about precipitation.
No, like a particle, they don't dissolve, they don't contribute for electrical conductivity, right? But when you have a solid as a dissolved type, it contributes your electrical conductivity so that you have a total dissolve. Because we don't know exactly inside, it's not only iron, it's not only, there are some organics, some other compound, neutral, so they are also contributing. So we just say solid, total dissolve solid.
This charge helps us in flocculation and
Right,
sedimentation.
right, yeah, right.
When we do the dosing and it mixes,
You're right.
the lighter will come up and the heavier will settle down.
Absolutely.
So we scrap the sediment and take all those flocks.
Yes, right.